Hi everybody, my name is Edgar. I'm a PhD student in material science at the Physics Institute of the Autonomous University of Puebla in Mexico. I hope you find very interesting my work and thanks for watching.
Well, the name of my work is a study of the structural, optical, and electronic properties of bismuth-doped copper antimony sulfide in films developed by chemical bath deposition. As introduction, the material we are investigating is copper antimony sulfide in its chalcocybate phase. This material has very attractive properties for use in solar cells. Among its most important properties, we have a low melting point, high absorption coefficient, band gap suitable for use in solar cells. The band gap can be modified by adding bismuth or for antimony, p-type conductivity, and it has abundant and non-toxic elements. Despite its promising properties, the maximum energy conversion efficiency reached by the heterostructure with this material as absorber layer is 3.22%. Methodology. The methodology consisted of making baths with different amounts of bismuth nitrate to obtain the desired stoichiometry formula. A specific sequence of reagents was added until 100 milliliters of solution was obtained. Subsequently, the previously washed glass substrates were immersed in the bath for 17 hours at 35 Celsius degrees. Finally, a thermal treatment was carried out at 350 Celsius degrees in a nitrogen atmosphere for 30 minutes. Results. Here we can see the X-ray diffraction results for each sample based on its bismuth content. We can observe that in the case of the pure sample and below bismuth content, only the chalcocybate phase is present. However, higher amounts of bismuth favor the appearance of secondary phases. We use Raman microscopy to confirm the results obtained by X-rays. Similarly, we can see that a low concentration of bismuth only chalcocybate vibrational modes are present. Again, as the amount of bismuth increases, the appearance of another phase is promoted. The vibrational mode at 346 Raman shift belongs to the Famatinate phase. For these reasons, any changes in the structural and optoelectronic properties could be attributed to the presence of these secondary phases rather to the incorporation of bismuth into the crystal lattice. In this table, we can see the atomic percentage of each element in the different samples. In all cases, there was a deficit of antimony, since the expected atomic percentage for this element is 25%. On the contrary, there was an excess of copper, since its expected atomic percentage is 25% as well. In the case of sulfur, in all the cases, all the samples, a percentage of 50% is observed. Finally, very little bismuth was detected, far from the expected values. We now turn to a brief morphological analysis. On the left, we have the sample with a bismuth, that is pure copper antimony sulfide. Its morphology consists of large polyhedra of the surface and a granular bottom. On the right, we have the sample with the highest concentration of antimony. We see that it is a different morphology from the previous one, purely granular, more compact, and dense. This change in morphology may be due to the fact that at this point we had more secondary phases present, so the initial morphology no longer prevails. Diffuse reflectance spectroscopy shows that all the samples present great absorption in the visible region of the electromagnetic spectrum. From this information and using the Kubel-Kamun formalism, we calculate the band gap for each of the samples. The trend is for a decrease in the band gap as the amount of bismuth increases. In the case of the electrical properties, we see a general tendency for carrier concentration to decrease. On the contrary, the tendency of carrier mobility tends to increase. This inverse relationship is because a lower concentration of carriers allows less carrier recombination, which in turn translates into higher mobility. As conclusions, we have managed to reproduce the deposit of copper antimony sulfide by chemical bath deposition. However, the incorporation of bismuth by antimony was not possible. In addition, the presence of this new element favors the formation of secondary phases. In this way, all the changes in the optical, morphological, and electrical properties cannot be attributed to the incorporation of bismuth. To confirm or discard the incorporation of bismuth into the crystal lattice, in the future, we will perform X-ray photoelectron spectroscopy. Here you can see some references for this work. And I'm grateful to CONACYT for extending the PhD scholarship in the material science. This all, thank you very much for your attention. See you.